Hello class. In this video I'm going to be discussing some philosophy of science. We already looked at a little bit of that. For example, we know some of the assumptions of science, that theories are underdetermined. We're going to take a look at three specific approaches to philosophy of science. One that was problematic and two that have some impact on how we understand science today. Just in general, philosophy is kind of an underpinning of other disciplines. Philosophy looks at how other disciplines do what they do. So there's a philosophy of science, a philosophy of math, a philosophy of sociology, psychology, whatever you like. There's even, in a way, a philosophy of philosophy, or it's called metaphysics. But that's beyond the confines of this course. But in any case, we're going to take a look at a few different approaches to philosophy of science and how they've affected the way that we view science today. The first approach to philosophy of science that we're going to take a look at is known as logical positivism. And logical positivism was a movement in the early to mid 1900s that said that science is the measure not only of truth but of intelligibility, meaning that if something was not scientific, if something couldn't be tested scientifically, it wasn't even a meaningful thing to say. So saying something along the lines of God is perfect or God is love are the equivalent to just babble, just rah. In terms of this view, those mean the same thing. And they relied on what they called the verifiability criterion to make this claim. And the verifiability criterion essentially just said that if you can't test something empirically via scientific means, then it is meaningless. So this is a very strict approach to sort of science being the measure of all things. And it was an attempt to sort of lay a foundation for truth and meaningfulness. However, it ran into some pretty significant problems, which we will take a look at in a second. Today, logical positivism is accepted by essentially no one, at least no one in academia. And there are three main reasons for that. First is, under logical positivism, science has no explanatory power. Science can't explain things because explanations are not the sorts of things that you can do empirical tests on. They're ideas. They're something beyond the physical world. Therefore, they were thought to be meaningless by the positivists. And that is a major part of the scientific enterprise. That's why scientists are doing the work that they do. They want to explain the world around them. So if a theory in philosophy of science takes away the explanatory power of science, it has failed at a fairly fundamental level. Another problem with logical positivism is that the assumptions of science were unfounded. Those assumptions that we already took a look at, we have no reason to believe that those are true. We have no reason to think, for example, that the universe is governed by laws or that the universe is uniform. And since we can't prove that via empirical methods, those assumptions were left unfounded. And lastly, and most problematic from a philosophical point of view, was the fact that logical positivism is internally contradictory. And it's internally contradictory because their verifiability criterion that they wanted to say was the measure for something being meaningful can't be subjected to empirical tests. So if you accept their verifiability criterion, then you have reason to reject their verifiability criterion. This in philosophy is known as cutting off the branch on which you're sitting. So a common example is if someone makes the statement, there is no absolute truth. If you say that, you are affirming an absolute truth, namely that there is none. So if you believe that there is no absolute truth, you have reason to reject that very belief, and you sort of go round and round in circles. You're stuck in a feedback loop, so to speak. So these reasons and others led to the downfall of logical positivism. We'll now take a look at two philosophers of science that have greatly impacted the way that we look at science today. The first prominent philosopher of science that we're going to take a look at is named Karl Popper, and his most famous idea is the idea of falsificationism. Falsificationism says that in order for something to be scientific, it needs to be potentially falsifiable. So there needs to be some way, at least in theory, of showing that it's false, or at least some way of testing whether it's false. So this idea, falsificationism, defines the purpose and the scope of science. And when I say that, I mean it shows that the purpose of science is to try and disprove theories. So we have these theories and we're continually putting them to the test. And if they pass, that's great. If not, then we need to revise them in some way or come up with a new theory. So that's the purpose of science and the scope of science. So if a theory is not empirically testable, it's no longer scientific. If there's no way for it to be false, then it's outside of the realm of science. So people can say strange things like there are millions of invisible leprechauns running around, and they're the reason that the sky is blue. You can believe that if you feel like it, but that is not a scientific statement because in the theory you can't detect the leprechauns, they're invisible, and presumably they put something else where you can't detect them with X-ray vision or whatever. This falsificationism has a big impact on how we view science, how we see the limits of science. However, it can be taken in a fairly radical way that can become problematic. So one way that this can be interpreted is to say that no theory is any better than any other, so long as the theory is internally coherent, because you can always sort of make revisions to try and save a theory. So if, for example, you wanted to believe that the Earth was at the center of the universe, you could accept Tycho Brahe's way of looking at the stars. He's a man that we'll talk about in a later date when we talk about the Copernican Revolution. But he was the last major astronomer to believe that the Earth was at the center of the universe, and he came up with a very elaborate system for explaining all of these anomalies that eventually led to our understanding that the sun is at the center of our solar system. But if you want, you can accept his theory. You just need to sort of put in a bunch of other outlying factors to correct for things. So you can't ever disprove internally consistent theories, so all of them are just as good as any other. Since Popper wanted to say that you never prove theories true, all you do is disprove theories, this does not seem to be the case in science. There are theories that seem to be proven better than others, so I would suggest that we reject this radical view of Popper that all internally consistent theories are as good as one another. And another sort of radical interpretation of Popper is that science is merely subjective, and this follows from the other, that all theories are just as good as any other, as long as they're consistent. If that's the case, then science is just scientists picking the theories that they like and rejecting the theories they don't like. This doesn't seem to be fair to the history of science. It does seem like we've gained a better understanding of the world around us, and there's all sorts of evidence for that in the increase in technology, medicine, etc. So the takeaway from Popper, the important things to remember are that scientific theories need to be open to empirical testing, needs to be some way to show that they could be false, and that science is always open to revision. We can be really sure about things, but in the end we might turn out to be wrong, as they were right before the quantum revolution, for example. So science is an ongoing enterprise, and it's always good to be asking questions, to be challenging, That's what makes scientific theories better and stronger. The second prominent philosopher of science we're going to take a look at is Thomas Kuhn. And Kuhn was the guy who came up with the idea of a paradigm and paradigm shifts, something you may have heard about. And according to Kuhn, a paradigm is generally a worldview, and in terms of science, a realm in which scientific work is done, and a paradigm shift is moving from one paradigm to another. So the reason that a paradigm shift happens is that a number of anomalies or unexplained data will sort of crop up in a paradigm. It will eventually lead to people questioning sort of the core beliefs of the paradigm that they find themselves in. There will then be a paradigm shift, a sort of new understanding of the world. And this has led to the idea that science progresses via revolution rather than evolution, meaning that science has these periods where it's kind of going along, progressing some, but not maybe progressing all that much, and then all of a sudden there will be a leap in understanding, a paradigm shift, and then you will continue along. So this is called normal science, the part where it's only progressing a little bit, and then you have the paradigm shift, where a lot of understanding is gained all at once, and the way that we see the world is altered drastically. So the quantum revolution is the most recent example of a paradigm shift in science, where all of these things happened that caused us to question just the very basic nature of the world. For example, the distinction between waves and particles. Before we thought they were distinctly different things. Now we think that everything is made up of both waves and particles. So these paradigm shifts happen, and they're just a dramatic shift in the way that we view the world and a dramatic increase in our scientific understanding of the world. As with Popper, there is a radical way of interpreting the things that Kuhn is putting forward. So one of those radical interpretations is that there's no progress in science. Each paradigm is just a different way of looking at the world, but we're not actually gaining more understanding about the world. There's just different ways of seeing things, and then there will be some problems with that way of seeing things, so we'll look at a different way, a different worldview, but neither of them are better or worse, they're just different. Another radical interpretation is saying that paradigms are incommensurable, meaning that you can't actually talk between two paradigms. So, for example, as people who live in a quantum paradigm, a paradigm with quantum physics, we couldn't meaningfully communicate with someone from the time of Isaac Newton, because all of our words have different meanings now. They refer to different things, so therefore we can't actually communicate sort of across history. And ultimately, the radical interpretation of Kuhn says that science is just a reflection of a particular culture, what scientists like or don't like. So as with the radical interpretation of Popper, I think that this is problematic. I do think that there's good reason to think that science has progressed if we just look around us. And Kuhn, this at least radical interpretation of Kuhn, runs into a problem because it can become internally inconsistent. So if we want to say that Kuhn has discovered this deep meaning about the world and the way that science progresses, that it progresses via paradigm shifts, we also need to say that Kuhn was writing in a particular time, in a particular paradigm, but this radical interpretation seems to think that he can somehow get outside of his own paradigm to view the entire history of science, and his own theory says that he can't do that. So, as before with the logical positives, if you accept this radical interpretation of Kuhn, you then have a reason to reject it. because it is paradigm laden itself. So I think that we ought to not accept this radical interpretation of Kuhn, but that we can learn significant things from Kuhn. One being that science is not wholly objective. Science is something that comes out of a particular culture in a particular time, and we need to take that into account when we're viewing scientific theories. Science also does seem to progress via revolutions, that there will be minor progress and then all of a sudden just an outpouring of scientific knowledge and discovery. And lastly, that we need to check our biases, whether in science or really anywhere else, and just realize that we are a part of a particular worldview, particular paradigm, whether it's scientific or cultural or whatever other adjective you'd like to tack on there, that we come out of a particular time and place with particular presuppositions, and that we shouldn't just accept those presuppositions without thinking about them, that we should be critically evaluating those presuppositions, whether they're scientific or otherwise.